Chapter 7 of your textbook covers the topic of systems of equations. A system of equations is a set of two or more equations that are to be solved simultaneously. A solution of the system must also be a solution of every equation in the system. In this course, we will discuss three methods of solving systems of equations: graphing, substitution, and elimination. Although these methods can be applied to other types of systems, in this class we will focus primarily on systems of two linear equations. Section 7.1 of your textbook deals with the graphing method for solving systems. To solve a system of two linear equations by graphing, we will graph both lines on the same coordinate plane. The solution to the system is the ordered pair that is the intersection point of the two lines. To understand why this is true, let's look at the example shown on the slide. The blue line is the graph of the equation y equals x minus 1. Remember that a line indicates all the solutions of an equation. So every ordered pair that falls on that blue line is a solution of that equation, y equals x minus 1. The red line is the graph of a different equation, the equation y equals negative 2x plus 5. And all the points on the red line, all those ordered pairs, are solutions of that equation, y equals negative 2x plus 5. We can see from the graph that there's only one point where those two lines intersect, the point 2, 1. Since that point lies on both lines, it is the solution of the system because it is a solution of each individual equation in the system. We can verify that this point is a solution of each individual equation by substituting it in to the equations. If we substitute the point 2, 1 into the equation y equals x minus 1, we obtain 1 equals 2 minus 1, which is a true equation. So this is a solution of that equation. Similarly, if we substitute into y equals negative 2x plus 5, we obtain 1 equals negative 2 times 2 plus 5, or 1 equals negative 4 plus 5. Since this is also true, the point 2, 1 is a solution of this equation as well. Let's look at some examples of how to solve systems by graphing. Our first example is a system of two equations, 2x minus y equals 6 and y equals negative 3x plus 4. To solve the system by graphing, we first need to graph these equations on the same coordinate plane. Let's look at our first equation, 2x minus y equals 6. We can graph it by isolating y and using slope-intercept form, or simply by leaving it in its current form and identifying the x and y intercepts. To find the x and y intercepts, remember, we set each variable equal to 0 and solve for the other variable. So to find the y-intercept of the line, we set x equal to 0. In this case, the equation would say 0 minus y equals 6, or negative y equals 6. Now we could multiply both sides of the equation by negative 1 to obtain y equals negative 6. This means the y-intercept of our line is 0, negative 6, and we can plot that point on our graph. To find the x-intercept, we set y equal to 0 in our equation. In this case, we would have 2x minus 0 equals 6, or 2x equals 6, and dividing both sides by 2, we obtain x equals 3. So the x-intercept is the point 3, 0. Now we can use those 2 points to form the graph of our line. And now to find the solution of the system, we need to graph our second equation. Equation 2 is y equals negative 3x plus 4. This equation already has y isolated. It's already in slope-intercept form, y equals mx plus b. In this case, we can see the slope, m, is negative 3, and the y-intercept is the point 0, 4. So let's plot that point 0, 4, and then using rise over run, in this case negative 3 over 1, we count down 3 units and over to the right 1 unit to find the second point. We can continue doing this down 3 and over 1 as many times as necessary, then connect the points to show the graph of the line. Having graphed both the lines on the same coordinate plane, we can see clearly that the intersection point is the point 2, negative 2. So that is the solution of our system. Let's look at a second example. In this case, our first equation is x plus 2y equals 6. The y-intercept of this equation would occur when x equals 0. So we would have 2y equals 6 or y equals 3. So the point 0, 3 is our y-intercept. The x-intercept of the equation occurs when y equals 0. So we would have x equals 6. So the point 6, 0 is our x-intercept. Connecting these points, we obtain the graph of our first equation in our system. Let's move to the second equation. Y equals negative 1/2 x plus 5. It's in slope-intercept form, so we can identify the slope as negative 1/2 and the y-intercept as the point 0, 5. So we mark that point 0, 5 on the graph and use rise over run to move down 1 unit and over 2 units, down 1 and over 2 as many times as necessary, and connect the resulting points to form the graph of the line. Now as we inspect this graph, we can see that these two lines are parallel. They have the same slope, so they will never intersect. Since there is no intersection point, we would say there is no solution to this system of equations. There's no ordered pair that makes both equations true simultaneously. Let's look at one final example and solve this system by graphing. Our first equation is 4x minus 3y equals 12. Let's graph by finding intercepts. The y-intercept occurs where x equals 0. So we have negative 3y equals 12, or y equals negative 4. That's the point 0, negative 4. The x-intercept occurs where y equals 0, so we have 4x equals 12, or x equals 3, which is the point 3, 0. Connecting those intercepts, we can form the graph of our line. Moving to our second equation, y equals 4/3 x minus 4. Well, we can see from slope-intercept form that the slope of this line is 4/3. The y-intercept is the point 0, negative 4. So we mark 0, negative 4 on our graph. And notice when we count a rise of 4 and a run of 3, up 4 units and over 3 units, we end up on that same x-intercept of 3, 0. And if we count again up 4 and over to the right 3, we obtain another point that appears to be on that same blue line. In fact, connecting these points, we see that the red line and the blue line actually overlap completely. They are, in fact, the same line. We have two equivalent equations. And when this occurs, we can see that every point on the line would make both equations true. So every point on the line is a solution. This means we have infinite solutions in our system of equations.